This is a short tutorial on trapezoidal method of integration. We will learn this algorithm without getting into too much mathematical details. The idea here is to understand the inner workings of this algorithm. Towards the end of this tutorial, we will implement this algorithm in Python and visualize this algorithm in action. So let's start. So here I've drawn a right trapezoid whose one side is y1, the other side is y2, and it has a width of dx. So as you can clearly see that the blue area is a rectangle and on top of it is a triangle in yellow color. And the idea here is to work out the area of this right trapezoid. So it's quite simple. The area of the rectangle is nothing but this y1 into dx, and the area of the triangle on top of it. So firstly, this height of triangle is nothing but y2 minus y1, which is what is depicted here. And then it is required to be multiplied by the base, which is dx, and half of it. So we are basically adding the area of rectangle and the area of triangle to get the overall area of this right trapezoid. And after rearranging these equations, what we come to is that the area of this right trapezoid is nothing but summation of y1 and y2 multiplied by half of dx. So this is the basic way in which we can calculate the area of a right trapezoid. So this is for a single trapezoid. Let's try to understand how do we go about calculating area if multiple trapezoids are stacked together. So in this figure, the idea is to figure out the area underneath this entire structure, which is comprising of 4 different trapezoids, all right trapezoids, each having a width of dx, and all of them are varying in their height. So the first one is y1, the second one is y2, the third is y3, and so on and so forth until we reach the final one, which is y5. So the basic area calculation that we did in the previous slide still remains valid. So this trapezoid, the first one in blue and golden color, is nothing but y1 plus y2 multiplied by dx divided by 2. Similarly, for the second trapezoid, y2 plus its adjacent side, that is y3, which is this one, y2 plus y3 multiplied by dx divided by 2. And then the next one, which is the third trapezoid, y3 plus y4 multiplied by dx divided by 2. And we can continue this way. So it's quite evident that some of the terms are getting repeated because some sides are getting counted twice. For example, if you see y2 appears here and y2 also appears here. Similarly, y3 appears here and y3 also appears here. And y4 appears here and y4 also appears in this term. And this is because one side of the trapezoid is common to adjacent trapezoids. So it's getting counted twice. For example, y2 comes into the calculation of this blue trapezoid, and it is also getting counted towards the area calculation of this reddish color trapezoid. So knowing that certain terms are repeating again and again, we collect them together and we list them down like this. And y1 and the last term, y5, they are the only terms which do not repeat. So we put them separately. So y1 comes here, y5 comes here, and all the repeating terms which are repeating twice are summed together and multiplied by 2. So in this manner, we can calculate and obviously we have to multiply it by dx divided by 2, which is common to all these terms. Also, if we see it in form of a see the structure in form of graph, so x-axis is on the horizontal line and the vertical line is the y-axis, which can also be a function of x. So we can write y1 as function of x1 and y2 as function of x2 and so on and so forth. So in this manner, we can calculate the area under a stack of trapezoids. So now comes the real challenge. What we are trying to do with this approach is that we have been given a curve, a function, say x square, and we are supposed to calculate area under this curve from 0 to 4, that is the limit of integration, by stacking all these different trapezoids under this curve from 0 to 4. So this is the first trapezoid. With only one trapezoid, we will not be able to approximate this x square curve that is depicted in black line. So obviously the error in integration term is going to be very large. Then we want to approximate this area under the curve using 2 trapezoids. So it will be a slight improvement, but still you can see that blue and yellow lines are overshooting the curve, x square curve. And then we are going to increase the number of trapezoids. So with each increase in trapezoid, if you see, the width of the trapezoid is becoming shorter and shorter, which is equivalent to saying that dx is tending towards 0, which is what is the definition of integration. So in the limiting terms, the x is as small as 0. So let's see how this whole algorithm works in Python and get a better visualization and hold of how to understand this particular algorithm. So in this section, we'll implement the trapezoidal method of integration. So let's start with defining the function. I will define a function f of x. It takes input x and returns x square. Okay, so this is our function, and let's plot it. For plotting it, I have to create an x-axis, so I'm going to use a function called linspace, which will start from, the x-axis will start from -2, it will go till 5, and it'll generate, say, 100 steps, 100 linearly spaced steps or numbers for me. So this is what is my x-axis, and let me plot my function fx by passing on these x values to the function. So let's see what happens. So let me just first show you what is x and what is fx. Fx is just an array of x-axis starting from -2 to +5, 100 numbers. And in response to this x-axis, when I pass it on to the function x square, it generates y values, which are here. So another 100 numbers, they get generated here. So instead of seeing it in this format, let me just make a plot of it. So my x-axis and my y-axis, and let me just plot it and show it to you whether this function is working or not. So let me just activate some general settings of the plot, and here we are. So we have x-axis starting from -2 going to 5, and we have implemented a function called x square, and this is the function. This is how it's behaving. Obviously, it's a quadratic function, so it has a convex curvature. So let me just remove this from here, and so let's define the limits of integration. So integration was starting from, the first limit was a, and it was going to 4. So this is the interval from 0 to 4. And now let's let the user input the number of trapezoids that he wants to use to approximate this curve, area under the curve. So I'll do one thing. I'll ask the user to input this. So input is enter the number of trapezoids, and this has to be an integer. So I'm going to make sure that this is an integer, or I can just do this integer and close the function. And once the user has entered the number of trapezoids that they want, we can calculate dx. So this is how it is calculated. Dx is the total interval, that is b minus a. In our case, it's going to be 4 minus 0, that is 4, divided by number of trapezoids that the user wants. So this will decide the dx. If you remember in the PowerPoint, I have shown it to you that the more the number of trapezoids, the lesser is the dx. So this is how the relationship is captured here. So so far so good. Let's now implement the trapezoid method. So if you remember, the area under the trapezoid was given by this formula, dx divided by 2 multiplied this whole term, which is comprising of the start of the limit, the end of the limit. This is add, and then there are some sum terms, intermediate sum terms, which get multiplied by 2. So we will implement this formula now. So let's first start implementing this middle terms. Let's just call it term 1. So even before we go there, we have to, every trapezoid has a start point and an end point. So we have to first decide that start point and end point. This is how we are going to do it, by defining it on x-axis. Same linspace method. So my first trapezoid will start at point A, which is a start of the integration. It will end at B, and I need n trapezoids. So because Python index starts from 0, I have to implement it by 1. So this is the number, this is the x-axis numbers that I will pass on to y-axis. So let me just pass on these x values. In a minute, I'll just show you what is happening here. So if you see print, I'll just print this out. So there's a small error here. This should not be here. So let's say I entered 4 trapezoids. Just a minute, I'll disable this plot. I don't need this plot as of now. So I just need, so I want 4 trapezoids, and my integration limit is from 0 to 4. So I will generate these 4 plots by passing on, the first trapezoid will start from 0, it will end at 1. And then the second trapezoid will start from 1, it will end at 2, and so on and so forth. And in this manner, I'll get 4 trapezoids equally spaced apart by dx. And dx in this case is 1. 4 divided by 4 is 1, and that's the reason why this interval is dx is 1. So this is as far as x values are concerned, and let's see corresponding y values. So let's print fxi also. So if you see, these all values will get squared here. Square of 0 is 0, square of 4 is 16, square of 1 is 1, square of 2 is 4, square of 3 is 9. So these are the outputs of the function. And if you remember what we had discussed in the PowerPoint, the algorithm works by aggregating the intermediate terms and then multiplying them by 2. So in this case, these are the intermediate terms. They will go. They have to be summed together, and this number and this number is required to be added later. So let's implement that part. So let me just call that as term 1. So even before I go there, let me just show you how to extract from this array fxi, how to extract these 3 numbers. So what I can do is I can go, there's indexing that I can do. So I want to start with the second element of the array and I want to exclude the last element of the array. So if I just print this, you can see that there is some issue. fxi array, what did it say? Too many sorry arrays, one dimension, two. Oh, sorry. So this, my fault. This should be this. Yeah. So now you can see that we have very successfully extracted these intermediate y terms from this array, and this line of code functions. So all I need to do is now multiply it by 2 and call it term 1, which is this term. This is what we have implemented so far, and we can actually verify it also by printing it. So let's say, let me print term 1, 4 trapezoids. So you can see that I have added together these terms and multiplied them by 2. So, oh sorry, I have not added them together. I have to add them together first. So this is sum, and now it will be the correct answer. Correct, 28. So if you see 9 plus 1 is 10, 10 plus 4 is 14, and 14 multiplied by 2 is 28. So this is what we have implemented. So this is correct now. Now we implement these two terms, the start of the function and the end of the function. So that's quite easy actually. Term 2, let's say. So we are going to add, we are going to pass on a value to the function, and then we are going to add that term 1 that we had, and then we are going to pass on the b value, which is a limit of integration. Let's see what this whole term 2 looks like. So here we are then. This whole thing was 28, and then we added 0 to it, so it remained 28, and then we added 16 to it, so it became 44, so it's functioning fine. And lastly, we need to implement this dx by 2 term. So what we have to do is, let's say, trapezoidal integration. So this is nothing but dx divided by 2 into term 2. So this is what is the implementation of this algorithm, and let's print this result. Integration result by trapezoidal method. Now this will be tr integ. So let's just see that. Let's just have 4 trapezoids. Let's enter, and by this method we are getting area under the curve as 22 when we specify 4 trapezoids. That's pretty good. Let's see what is the theoretical, what does it all mean. So what I can do here is that I can, let me just plot what I've done so far. Let me just activate my plot function, general settings again. So there you go. These are the linear approximations to the x square function, and I'm going to generate trapezoids under them. This is what is happening here. There are 4 trapezoids as user entered 4. So you have 4 sections here, 1, 2, 3, and 4. It will become more clear as we progress further. I don't need this plot, so I'll just disable it. Now let's see what does the theory say. So what theory says is that integration of x square is nothing but x cubed divided by 3. And when we consider the interval between 0 and 4, this is what is the area under the curve, 0 minus 4 cubed divided by 3, which is nothing but 64 by 3. This is the theoretical value of the integration. So let's see what is the by theoretical method, which is nothing but simply 64 divided by 3. So let's just do it again, and here we are. So this is the theoretical result. It says the area under the curve is 21.3, and by trapezoidal method we are getting 22, which is incorrect because we have chosen very less number of trapezoid to approximate this curve. So it will become clearer when we draw the plots. So let me just say, let's see what happens if I increase the number of trapezoids. So instead of 4, let's have 10 trapezoids. So you can see that the accuracy of trapezoidal method is increasing. Now it has become 21.44. Earlier it was 22, and it is reaching closer to theoretical value of 21.33. Let me just do it once more. Let's say this time I do it with 100 trapezoids, and okay, I disable these settings too, not required. So here we are. So if I have 100 trapezoids, I am approximating this area under the curve very closely, as accurately as given in the theoretical results, 21.33, 21.33. So as we increase the number of trapezoids, the dx tends to 0, the dx value becomes smaller and smaller, and the accuracy of this algorithm improves. Okay, so now let me just plot these trapezoids. So I have n number of them, so I will have to plot all of them. So for each n there will be a plot, and I'm going to use a function called fill between, which will color this. So it will be xi, the start of the first trapezoid, and its end will be at I plus 1. So this takes care, and these are the x values, and now we have to give the y values. So these are the y values of it, and I will specify a transparency of say 0.5. So let's see these results now. Let's hope it works. So let me just say 4 trapezoids. So here we are. These are the 4 trapezoids starting from 0 to 4, and as you can see, the accuracy is pretty poor. It is 22. The area under the curve is 22 as per trapezoidal method. If we, let me just zoom into this to show you the spillover of trapezoids. So let's say I just have only one trapezoid. Okay, so this is what happens. If you have just one trapezoid, it is overspilling. It is going above the x square curve, and it is not able to approximate this curve properly. That's the reason why the integration result is very poor. It says 32 is the area under the curve, whereas actually the area under the curve is 21.3. So very bad approximation by using one trapezoid. Let's see what happens when we have 2. So we have 2 trapezoids here. The accuracy has improved, but still not good enough because 2 are not sufficient. You see the dx is quite large here. Dx is of 2. So let's say what happens when we have 4. It has become better. Now we have 4 trapezoids under this curve, but still you can see that these colors are overspilling. They are going above the curve, and that's the reason why we have errors. Let's see what happens when we have 10 of them. So you see now, the number of trapezoids we use to approximate this curve, the integration accuracy keeps on improving. Let's say 50. So there we are. We are getting closer and closer to the theoretical value, and that's how this whole algorithm works. The more the number of trapezoids, the dx tends to 0, and the better is the accuracy of a trapezoidal method.